Hello everyone, we are Team Ice Cubes. Our chosen problem statement is Smart Water Pressure Management for Equitable Water Supply in Solapur Municipal Corporation. Solapur Municipal Corporation serves over 10 lakh citizens across multiple water distribution zones. However, the system faces major challenges like leakages causing water loss, tank overflows due to mismanagement, and unauthorized consumption leading to losses. Tailend and elevated areas faces low pressure supply causing uneven water distribution. This leads to inefficiencies, water wastage, and inequitable access across the city. Existing solutions and its limitation. Currently, Solapur uses a SCADA-based monitoring system for water management. While it enables real-time data collection and control, it is limited to monitoring and manual operations. It lacks analytics, fault detection, and predictive capabilities. As a result, the system remains reactive rather than the proactive in handling issues. Our solution transforms this into a proactive, data-driven solution with real-time analytics, detection, and prediction. Approach of our system. Solapur is divided into 8 zones across the city, consisting of both instrumented and non-instrumented areas. Instrumented areas are equipped with sensors, while non-instrumented areas are without sensors. Now, this is the overall video structure we will be covering in this video. We have already completed the problem recap, and next, we move into the mapping of objectives, functions, constraints, and the system architecture flow. Here, we have 4 core system features. We begin with the data integration and validation. Data is collected in 2 ways, from instrumented and non-instrumented areas. In instrumented areas, real-time pressure and flow data are collected through SCADA using RTU and PLC systems. This data is integrated into our system via API calls and stored in the database. In non-instrumented areas, we use an EPANET-based network model of Solapur. It takes hydraulic inputs like base demand, pipe length, and diameter to estimate flow and pressure, which are then stored and integrated into our system. To ensure reliability, we perform model calibration and data validation. The EPANET outputs are compared with real-time sensor data, and parameters like roughness are adjusted iteratively until deviation is minimal. This is validated using a graph, where both simulated and real pressure values at the same node follow a similar trend over the time. This confirms that our model is calibrated and the estimated data is reliable. Now let's move to challenge detection. We follow CPHEEO standards to define pressure thresholds and operational conditions. The challenges are categorized into 3 types: hydraulic imbalance, non-revenue water and loss detection, and operational failure detection. Let's start with hydraulic imbalance detection. In EPANET, tailend nodes show pressure around 3 meters, which is below CPHEEO standards. Our system detects these as low pressure zones and highlights them in a dashboard for corrective actions. Elevated areas. Similarly, elevated regions also experience low pressure. These zones are identified and flagged in a system for operator intervention. Sudden pressure drop. The system continuously monitors pressure trends using historical data. Any sudden drop is detected and alerted as a potential issue in that specific zone. Unequal water distribution. When 2 pipes in a same region show unequal pressure, the system detects it as uneven distribution and alerts the operator with zone-specific insights. Now let's move to non-revenue water and loss detection. Flow imbalance. When inlet and outlet flow does not match, the system detects a flow imbalance indicating possible losses in the network. Leak detection. By comparing sensor data across the regions, the system identifies abnormal flow differences and flags possible leakages zones. Burst pipe detection. A sudden drop in pressure along with abnormal flow variation is detected as a potential pipe burst and alerted for immediate inspection. Unauthorized consumption. When unusual flow patterns occur, especially during low demand hours, the system flags it as possible unauthorized consumption. Let's move to operational failure detection. Tank overflow. When inflow exceeds outflow beyond threshold levels, the system detects tank overflow and suggests corrective actions. These are the visual representations for better understanding. In real time, our system uses data-driven logic and historical analysis to detect and alert all such challenges proactively. Now let's move to smart pump automation. The system continuously monitors all zones using SCADA and detects pressure drops below threshold levels. Once detected, it diagnoses the issue and triggers a real-time alert on the dashboard where the operator initiates auto-adjust. The system then pulls live data, feeds it into EPANET, and simulates optimal pump set points. If all zones remains within same limits, then the set point is finalized and sent to SCADA, where pump speed is automatically adjusted. The system then validates restoration using live feedback and continuous monitoring dynamically. Now let's move to forecasting and decision support. Our system uses historical data to predict key risks and enable proactive actions. First, low pressure risk forecast. The system predicts pressure drop in advance. For example, pressure is expected to fall to 8 meters in the next 6 hours below the required 12 meters. Next, tank overflow analysis. By comparing inflow and outflow trends, the system predicts outflow time and suggests actions like reducing inflow or opening outlet valves. Then, pump performance and degradation prediction. The system tracks performance over time and alerts before reaching critical failure thresholds. Finally, burst risk prediction. By analyzing pressure fluctuations and flow surges, the system predicts high burst risk with a failure window and alerts for immediate action. These are sample visual representations of predictions. In real time, the system continuously learns from historical data and performs intelligent forecasting. Architecture or system flow. This is the overall system architecture and workflow. Data from both instrumented and non-instrumented areas is integrated into our database. The system processes this data for detection and analytics and further performs predictions. All these layers are unified into a single dashboard providing zone overview and real-time monitoring. So with this, the mapping of objectives, functions, constraints, and the system architecture is completed. Now let's move to the live demonstration of our dashboard. This is a smart water pressure management system designed for authorized SMC officers and operators. Operators log in using secure credentials, ensuring controlled and authorized access. After login, users select their preferred language such as English, Marathi, or Hindi for ease of use. At the top, the dashboard shows system status, time, language switch, simulate option, and an emergency stop for safety control. The simulate feature allows the operator to safely practice scenarios like low pressure without affecting live operations. We display key system matrices including operational status, last update, weather, backup power, active leaks, and critical alerts. All 8 zones are listed with real-time pressure, flow, pH, losses, and status, along with suggested actions for each condition. We also provide overall network summary, reservoir levels, and water quality for complete system visibility. Live pressure trends across zones and flow trends from pump stations help track fluctuations and overall system performance over time. In the Zones tab, users can view residential, commercial, and industrial areas with real-time parameters and guided actions. The pump station section shows performance and allows EPANET-based auto-adjust where pressure is safely optimized using VFT control. The Alerts tab provides live alerts and detailed diagnostics and maintain history for tracking and analysis. In forecasting, the system predicts future risk using latest data and suggests proactive actions like scheduling or ticket creation. The pipeline network maps gives a real-time visual of all zones, helping operators identify exact location of the issues. The valve control feature allows the operator to remotely manage valves for faster response and control. Finally, system reports provide detailed zone-wise insights and can be exported for monitoring and decision-making. This completes the live demonstration of our system, showcasing real-time monitoring, intelligent control, and proactive decision-making. Now let's move to the technical feasibility of our system. Our system works directly with the existing SCADA setup through API integration, ensuring zero disruptions to current operations. Using EPANET simulation, we cover all non-instrumented areas, providing complete visibility across all zones without additional sensors. All pressure values are validated against CPHEEO standards, ensuring safe and regulation-compliant water distribution. Pump automation is triggered only after EPANET pre-simulation confirms safe pressure conditions across all zones. The system is scalable across all zones, and new sensors can be easily added without modifying the core system. Our solution runs on existing government-grade computers already available at SMC, requiring no special hardware or additional infrastructure. Now let's move to the deployment plan for SMC, which is divided into 3 phases. Phase 1 pilot deployment, month 1 to 6. We begin with SCADA API integration to enable secure real-time data flow. Next, we develop and calibrate the EPANET model for pilot zones. The complete monitoring dashboard is then deployed for real-time insights. VFDs are installed at pump stations to enable automated pump control. Finally, operators are trained to use alerts, automations, and reporting features. Phase 2. Full city rollout, month 7 to 15. The EPANET model is expanded to cover the entire city network. Complete SCADA integration ensures full real-time data coverage. Challenge detection is activated across all zones for continuous monitoring. Citywide pump automation is enabled with validated control actions. Forecasting and proactive alert systems are activated for preventive operations. Phase 3. Optimization and expansion, month 13 to 24. EPANET models are continuously recalibrated using latest sensor data. Strategic sensor expansion is done at critical network junctions if required. NRW detection reports are generated to track losses and improvements. Finally, a full performance review evaluates efficiency, pressure equality, and the savings. Now let's move to the cost estimation for implementing this system. The overall cost includes software development, SCADA integration, EPANET modeling, dashboard development, deployment, and VFD installation. This is one-time implementation with scalable expansion, ensuring long-term operational saving and efficiency. Now let's move to the innovation part of our system. Hybrid data coverage. We combine real-time sensor data with EPANET simulation to achieve complete network visibility even in non-instrumented areas. Condition-based pump automation. Our system validates every pump action using EPANET simulation before execution, ensuring automation without compromising network safety. Model calibration validation. We do not rely on simulation blindly. Our model is calibrated with real sensor data, ensuring high accuracy and reliability. Neighbor-based anomaly detection. Using network intelligence, we detect leaks and anomalies in non-sensor areas by comparing neighboring sensor data. Reactive detection system. Unlike traditional systems, we detect issues early using trends and patterns, enabling action before failure occurs. Operator training simulator. We provide a simulation environment where operators can train on real scenarios without affecting live operations. Unified operation platform. All monitoring, detections, automations, and reportings are integrated into a single dashboard for complete control across all zones. These visualizations show how our system solves the problem with an optimized solution. In real time, our system continuously analyzes the data, detects issues early, and takes proactive actions. With this, we ensure equitable, efficient, and reliable water distribution across all zones, transforming Solapur into a data-driven city with intelligent water management. Thank you.